Welcome back to Advent of Code 2021, day 8. Okay. Welcome in, Amaro. Yeah, I got 7 done yesterday. They weren't too difficult, like 20 minutes each or something. Alright, day 8. Day 8, 7-segment search. You barely reach the safety of the cave when the whale... Oh yeah, we're being chased by a whale. Whale smashes into the cave mouth, collapsing it. Sensors indicate another exit to this cave at a much greater depth. Basically, this whole 2021 is themed around basically Subnautica. We're in a submarine exploring places. What you're doing, Isles. So did the expansion add like a new world, essentially? You notice that the 4-digit 7-segment displays... That's a 7-segment display. I remember coding for these. It's always quite confusing. Needs a lot of logic gates. Each digit of a 7-segment display is rendered by turning on or off any of 7 segments named A through G. So to render a 1, only segments C and F would be turned on, the rest would be off. To render a 7, only segments A, C, and F would be turned on. Yeah, okay. The problem is that the signals which control the segments have been mixed up on each display. The submarine is still trying to display numbers by producing output on signal wires A through G, but those wires are connected to segments randomly. Oh no. Worse, the wire segment connections are mixed up separately for each 4-digit display. Hello, DJ. All of the digits within a display use the same connection set. So you might know that only signal wires B and G are turned on, but that doesn't mean segments B and G are turned on. The only digit that uses 2 segments is 1. So it must mean segments C and F are meant to be on. Right? With just that information, you still can't tell which wire BG goes to which segments CF. Wait, so... So they're talking about if we're trying to display a 1. But what is it we actually see? We just see the segments, right? We don't see what the wires carry. So if we see... We see 2 segments light up. We know a 1 was pressed. But it's wired, they're wired to the wrong segments. Okay. For each display, you watch the changing signals for a while, make a note of all 10 unique signal patterns you see, and then write down a single 4-digit output value. Four-digit output value. That's more than... Or... What? Using the signal patterns, you should be able to work out which pattern corresponds to which digit. For example, here's what you might see in the single entry in your notes. Okay. Let me just look at the input so I understand what... Okay. These are entries. Single 4-digit output value. Oh! I see. It's on the right. Okay. So the pipe symbol is separating the, that's the 4-digit output value. Okay, so you look at the signals, you see, you identify all 10 unique signal patterns, doesn't matter the order, so you see 10 different possible lighting up of the segments. And just looking at that, we can see that's the 1, because 1 is the only one with 2 segments lit up. So 1 is corresponding to AB, and like DAB is using the same 2 as 1. So that would mean it's a 7. Because plus 7 is the only one that uses 3 segments anyway. Okay, fine. So I get what that means. So each entry consists of 10 unique signal patterns, pipe delimiter, and finally the 4-digit output value. So what do we want to do with the... What's the point of the 4-digit output value? Within an entry, the same wire segment connections are used. The unique signal patterns correspond to the 10 different ways the submarine tries to render a digit. You should be able to work out which combination of signal wires corresponds to each of the 10 digits. Okay, we can deduce stuff. Then you can decode the 4-digit output value. So we just want to know what the 4-digit output value is in terms of decimal. All the digits in the output value use 5 segments are more difficult to deduce. For now, I'll focus on the easy digits. Consider this larger example. Because the digits... Basically, they added the Dark Island artifact, and that one unlocks extra puzzles on the other islands. Okay. So they're giving us... Okay, so we're only focusing on these 4 digits now. So we know a 1 means there's 2. A 4... 1, 2, 3, 4. A 4 has 4. And is it the only one that does? Yeah, it is. Okay. and 7 or 8. Oh, so it... Okay, part 1 is literally just count... Count how many of these have 2, 3, 4, or 7. Okay, fine. We'll just do that then. Okay. Okay, so for now we just want to say left, right equals line dot strip dot split on pipe with 2 spaces. Is that 1 space? Yeah. So right equals, let's just split it into the 4 tokens. So okay. So for now we can just so it's got to be what, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. $375. All right. Part 2. Well, that was really easy. Just count the number of those token sizes. Through a little deduction, you should now be able to determine the remaining digits. Consider again the first example above. After some careful analysis, the mapping between signal wires and segments only makes sense in the following configuration. So the unique signal patterns would correspond to the following digits. So we're basically solving a Sudoku. do that. So you're told the 10... Okay, so there's 2 layers to this. We have to work out what the digits are. Work out what the Y is. Well... Why do they not give it in alphabetical order? Does the order matter? I don't think it does. So it's equivalent to saying A, B, C, D, E, F, G, isn't it? Should be. So we have to order them. Okay. We don't have to work out what all of them are. We just have to work out what those 4 are. So they might give us examples where it's impossible. Although I think it probably is usually possible to work out what everything is. But you only need to work out what these 4 are. So whenever it's 2, 3, 4, or 7, we know what they are. I guess we want to make some maps. So like 0, 6, 1 is 2. Oh, okay. Let's just create some maps here. So let's make a map which says how many, given a number of segments, which digits this could be. So it'd be like possible digits. So it'd be like 2 maps to 1. It can only be 1 in that case. 3 maps to 7. 4 4. What was that one? That maps to 4. Um, 2, 3, 4. Let's see. 0 is 6. 2 is 1, 2, 3, 4, 5. So 5. That can be 2, 3, 5, 2, 3, or 5. Six can be... Zero, 6, 9. And then of course 7 can only be 8. Okay, so basically we know what these 4 are, and if we get these 2, then there's 3 possible values they could be. Okay. Okay. So generally there will be... So in our list of 10, there will be 6 that we don't know. 4 that we do. 3 of them of size 5, 3 of them of size 6. And that's always going to be the case with no other information. And then when you consider the segments... I mean, I think there's some quick rules we can use to immediately deduce, like, which one is the... Okay, let's have a look at this. So we know what the 1 is, and it has the C and the F. So if we're trying to distinguish between 5, 2, 3, and 5, of those 3, the only one that uses the C and F is 3. So we can immediately identify which one's the 3. It has to contain the same segments that the 1 did. So that tells us which one's 3. And it also tells us which one's 6, because it's the only one without the C and the F. So we've just got a rule. We've got a rule that identifies 3 and 6. Okay, that's a start. So once we've got 6, we would know the other two are 0 and 9. And for that, we just choose the one which has the 4, because 9 contains a 4. So we choose the one that contains the segments of 4, that identifies 9, and then we also get 0. So what's left? We just need to distinguish between 2 and 5. And for that... what's the easiest way to do that? Just... Well, 5 is contained in 9, and 2 isn't. Are we done? That is one process we can do to identify every single digit. Yeah. Then we just have to code that. Not too tricky. Okay. That's actually easier than I thought it would be, because I thought we might have to do something a bit more Sudoku-like. But if there's a process which definitively, like, rules them out, then you kind of have to do something a bit smart. But in this case, I think we do have such a process. We don't even really... yeah, okay, we don't... Okay. So, let's write a method. Given an entry, which is the list of strings, just find a mapping No, we want a decoding. We want... that decoding, which just says this string is this number, and so on. Alright. Also, we should really sort them so that we don't have an issue with order. So let's assume we're given that sorted. Right, so we want... oh, we don't need to even do that. We can use set difference and stuff, set operations to do it. So yeah, we don't need to sort them. So the coding is that. All right. So we look through the entry. All right, let's just fill in the 1, 4, 7, 8. Okay, so for digit in entry, if length digit equals 2, then decoding is 1. If it's 3, then it's 7. Otherwise, if it's 4, it's 7, it's 8. Okay, so we do a first pass so that we know where the 1, the 7, the 4, and the 8 are. And then on the next pass, we should be able to work out everything else, given that we already know those. And we want to make a note of the 4, so let's say 4, just create a variable called 4 equals digit, and create a variable called 1, because those two are special that we'll be using to deduce other things. Alright. Now that we know those, we'll make a second pass through all the digits. For digit in entry, if it's 5, we know we're either 2, 3, or 5. Okay. So what was the first step? First we check if it contains 1. If it contains 1, that means it's a 3. So if set, so we turn 1 into a set, and we do contains 1. Is that right? No, you don't do that. What do you do? I gotta look this up again. Set.is subset. So if set1 dot is subset of set digit, then decoding digit equals 3. Okay. elif, and then how did we distinguish the 2 and the 5? Oh, we used the 9. Well, instead we could... that means we have to do a third pass. Instead, we could just work it out now by saying, okay, so... we use the 4. We just find the... how much in common 4 has with 5, so it should be 3. And with 2, it's just 1. Oh, okay, okay. So we take the intersection So we say elif set for intersect. How do you intersect sets? It's that, right? I've got to look this up. You can just do dot intersect as well, but what's the quick method? Yeah, it's the ampersand. So step 4 and set digit length is 1. Then it can only be a 2. Because it's just that middle bar. Okay, so that identifies those. And then we're on to the 6. Alright, now for this one, we check if it contains 1 again. That would... no. Yeah, that will identify the 6. So... if 1 is not a subset of it, then that means it's a 6. So that in that case we've just got 0 and 9, and 9 contains the 4. So elif set 4 dot is subset of that, then it's a 9. Else it's a 0, and that's everything. 2 passes. Can be done in 1 pass. Well, not really, because you need to know where the 4 and the 1 are, so you need 2 passes, really. Okay. Now what do we do with that? So we want to first just fully decode the left-hand side, even if we don't need all the digits. And then... alright, so... okay, left... so... left equals left dot split. And we never need to sort them because we're using set operations anyway, so it doesn't matter if they give us AD and DA or whatever. It looks like... yeah, they do look. So that there's AD here, but then there's DA, DA. So the order, they do mix up the order here. Left equals left dot split. Now we want decoder equals solve left. This has to be defined beforehand. Token and write result 1 plus equal that. So what is the ultimate thing they want us to compute here? To code the 4-digit output values, what do you get if you add up all of the output values? So first we have to create a string to contain the output. So let's do part 1, and we output plus equal decoding. No, wait. The order does matter here. Unless they always kept the order between the left and the right side, but I don't see any reason why they... We shouldn't assume it. A, D, B, G, C, F. A, D, B, G, C, F. Yeah, they do actually mix up the order. Fine. That means when we do the decoding, we have to so we take the sorted X. So now the decoding should be sorted. Hopefully I've done that right. Output plus decoding, and then we'll have to do string sorted token. Then result to plus equal int the output. Just comment that out for now. I should have... Okay, fine. Oh, that's not how that works. How do you sort a string? Oh, you have to... Sorted X would give a list, and then you got to do... Okay. That. Only concatenates string, not into string. That's a string. These need to be strings. Not. Or do we prefer them as digits? I don't know. It's a. They have numerical meanings. We'll return it as a digit, but here we'll have to just cast it to a string. Alright. Hopefully this works, because it's easy to get a few things wrong here. Nope, it's too high. I think the fact that this completes, so I think the idea of the process is correct. Just a mistake somewhere, I guess. So oh no, this is wrong. Oh no, that's right. That's right. 9 contains 4. Look at the diagram again. 9 contains 4, 0 doesn't. Yeah, that's right. Did we still get... Wait, so part 1 was 375. Yeah, that's the same. Now, the fact that it actually gets an answer at all really indicates that the error is just in this logic here, because what else could have gone wrong? Well, hang on. I could have... This bit could be some... sort of left us... So we are sorting them. Sorted token, yeah. Let me just print the outputs. That's what the outputs look like. They're all 4 digits. Uh-oh. Wait, no, that's fine. Wait, okay, so we've got those two the same. Does that happen? Yeah, it does. Yeah, that's right. Looks plausible. All right, we'll try the test example then. Six one two two nine. Why did you do this? Put them on separate lines like this, damn it. can't we get it as a... putting the test case in a different format to the... Alright. 61259. And we should be getting 61229. So we're very slightly off. Surprising. Okay. Let's go through the numbers. 8394, correct. 9781, correct. 1197, correct. 9361, correct. 4873, correct. 8418, correct. 4548, correct. 16, uh-oh. So we should have 1625. We got 1655. But the other two, 8717, correct. 4315, correct. So we got 1655. Should have been 1625. How did I distinguish between 2 and 5? I said that. Oh, I see the problem. What was my logic? So to distinguish between 2 and 5, I said that it has an intersection of 1 with 4. But if you actually look at the diagram... So if you try to intersect the number 4 with 2, it should be 2. And if you try to intersect 4 with 5, it should be 1, 2, 3. So it's 2 and 3. So if it's 2, then the answer is 2. So if that's 2, then it's 2, otherwise it's 5. 61229. Yep, okay. Hopefully that's right now. Otherwise we're in big trouble. All right. Stay 8. That was an interesting problem. They could have made it a lot harder if they made a like my process for solving it was a fixed number of steps. Like you can get every digit as long as you just follow this one process. But you could make it closer to a proper Sudoku where everything you look at can rule out certain options, and then there's no knowing how many cycles you have to go through, crossing out possibilities until you got unique ones, and then yeah, it could potentially be a very difficult problem. And I mean, yeah, the fact that it's a 7-segment display imposes a lot of restrictions, so I guess it's actually kind of hard to make it a bit more like a Sudoku, because you're already completely identifying 1, 4, 7, and 8 or whatever. There's no getting around that. And then there's not much left.